All right, welcome back, everyone. Today we have the collision theory and reversible reactions to continue on with our equilibrium chapter. We'll be starting on about the middle of page 3. We'll work to about the middle of page 4 here. So the first thing we're going to talk about is we're going to talk about the collision model. Small molecules must collide to react. However, only a small fraction of collisions produce a reaction. So why? What are factors that need to be considered for collisions? So we'll think about those. An example down here at the bottom is if you think of clay clumps thrown together gently, they don't stick, but if thrown together forcefully, they stick tightly together. So if you look here, speed helps with collisions and some sort of to produce a reaction. So we're going to look at what makes an effective collisions. Collisions must have enough energy to produce the reaction. So must equal or exceed the activation energy. So how much energy is needed for the reaction to occur to get started. And so collisions must also have the correct orientation. So if we look over here on the left-hand side, they have to hit where the bonds are going to form. So you need some sort of correct orientation for those favorable bond formations. And then also particles lacking necessary kinetic energy to react balance apart unchanged when they collide. So you need the kinetic energy to be sufficient in order to provide that some sort of energy that may be required for the reaction to occur. With the kinetic energy, remember we're thinking about speed. So remember particles with this to increase the kinetic energy, increase the speed of particles. So if particles moving really fast, we could increase the effectiveness of collisions. So let's look at the collision model a little further. The collision theory explains why some naturally occurring reactions are very slow. So if you think of carbon, oxygen, it's all around us in the atmosphere, but why doesn't fire just automatically occur? So an example is charcoal, which is made of carbon and oxygen. So usually when you're lighting your grill, maybe when during the summertime when you're having a cookout, you have to the carbon and the oxygen just doesn't ignite just how it is in the atmosphere right now. You have to produce some flame, maybe from a lighter or from a match of some sort, in order to give the in order to get that activation energy for the reaction to occur. So at room temperature, the carbon and the oxygen don't react based on the collisions, but if you give them some sort of energy from, say, the lighter, then you increase the likelihood of those collisions occurring by giving it some sort of energy. When we think about reactions, they can occur very fast, such as a firecracker, or very slow, such as the time it takes for a dead plant to make coal. So I kind of have an example over here of how coal is formed. So we have millions of years ago, we had plants in swamplands. Those swamps, those plants that are in there started to decay, got into the dirt. Over time, they have been exposed to high temperature and high heat, and rocks and other material have formed above them. And now, due to that high pressure and high heat, we now have coal. And it took millions and millions and millions of years in order for that coal to form. So that'd be an example of a really slow reaction rate. When we think about a rate is a measure of the speed of any change that occurs within a interval of time. So in chemistry, we're going to think about the amount of reactant changing per unit time. Factors affecting the rate. So we're going to have temperature. So increase in temperature always increases the rate of the reaction. So with temperature, the particles are probably going to be moving faster, right? So with faster particles, greater kinetic energy, we can get to that effective collisions. Surface area, increase in surface area increases the rate of a reaction. More likelihood of colliding. If you have a bigger surface area, you have more likelihood of colliding. If you're really, really, really small, you can miss those collisions. With concentration, increase in concentration usually increases the reaction rate. So if you have a higher concentration, again, you have a higher likelihood of colliding. If you have a higher likelihood of colliding, you have a higher likelihood of colliding with the correct conditions in order to produce a reaction. And also the presence of catalysts. Right, so we're going to dedicate the rest of this presentation to catalyst, a big portion of it. Wherein catalysts help speed up or help reactions move forward. All right, so they help lower the activation energy is what we'll get into. So we're going to look at catalyst now. So catalyst is a substance that speeds up a reaction without being consumed. So this is not consumed. The catalyst is not consumed in the reaction. So whatever catalyst you put in to the beginning of the reaction is the catalyst that the same amount you're going to get out at the end of the reaction, right? There's no consumption of the catalyst in the reaction. It speeds up the reaction by lowering the activation energy. When we think about the naturally occurring catalyst, we have enzymes in our body. It's a large molecule. The human body, an example here, the human body temperature is 37 degrees Celsius, much too low for the digestion reactions without catalyst. So we need catalyst or enzymes in order to break down food in our digestive system. Inhibitors can interfere with the action of catalyst. So if an inhibitor, if you look here at the bottom of the figure on the left-hand side, an inhibitor binds to the activation site. And so if the inhibitor is bound there, then the substrate, which would be some reactant that you put into the some reactant that you had, if it's not able to bind to the location, the active site, then it's not going to be able to have the enzyme's not going to be able to be effective. So an inhibitor binds to that active site, and then therefore the enzyme would be ineffective if there was an inhibitor. When we think about energy diagrams and endothermic, so remember endothermic energy is being put into the system. With this, if you look at with the use of a catalyst, if you look in the middle, it has the activation energy if we have no catalyst, but look how much smaller the activation energy is if you do have a catalyst. It lowers it. So you don't need as much energy with the catalyst in order to get the reaction to move forward. The same thing will also be true with exothermic reactions here. So with the catalyst, once again, the activation energy is lowered. So without a catalyst, you're going to need a lot more energy in order to get the reaction to occur. With a catalyst, you need less energy for a reaction to occur. It makes it more favorable. All right, now let's think about reversible reactions. So far in this class, we've been thinking about forward reactions, reactions that we've talked about specific. We had combination, decomposition, single replacement, double replacement, combustion reactions. Those are all forward, one-directional reactions that we talked about. But some reactions do not go to completion as we have assumed. They may be reversible. So reaction in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. So you're having products being formed, you're also having the reactants being formed, so it's going back and forth simultaneously. So they're both occurring at the same time. If we look here at the example, we have the forward and the reverse, so it's just the opposite. Usually we've been using one arrow. Now we're going to use a double arrow, which will be on the next slide here. So with a reversible reaction, we're going to use a double arrow, indicating that's going back and forth simultaneously. Both are being formed. All right. Also, in the chemical equilibrium occurs, no net change occurs in the amounts of the components of the system. They may not be equal, they may not have equal amounts of products or reactants, but the overall change or the overall amount of them is not changing. So if a product is formed, the same amount of reactants is formed, and it keeps going back and forth, but this with the same amounts being produced. So there is no net change in the amounts. I do have a diagram here on the left-hand side. So when we're looking at the rates of the forward and reverse reactions, they're going to be equal. So we have the forward rate, the reverse rate, and then at some point during the reaction, we're going to get to an equal rate, and that's where we have the equilibrium, where it's going back and forth both ways, but there's no net change in the amount. If we look down at the bottom graph, that's indicating that the amounts do not necessarily have to be the same, but at equilibrium, there's no net change in the amounts. So here, the reactants, there's less of them and more products, but once we're at equilibrium, the same amount is going to be consistent. There's going to be no net change in the amount. So they're going to keep going back and forth, but they're going to keep that same amount. So I have it drawn here that the equilibrium position may be shown. So you may be producing a lot of the products, very little of the reactants, but you're keeping that same amount the whole time. So when we think about reversible reactions, it depends on which side is favored. Almost all reactions are reversible to some extent. All right. So moving forward with reversible reactions, we'll look at conditions affecting equilibrium and what factors, if say certain conditions are changed, how does that affect equilibrium? So that'll be moving forward. How is equilibrium affected by certain factors?